Good morning, students. Today we are going to see the new unit, that is the unit number 4, work, energy and power. So in this, how these three are related, that we are going to see as first. So what is work? First of all, in generally the term work is we are seeing in our daily life in many contexts a work, that word, and work is nothing but the we have to do that as physically and also mentally. That means we are working physically and also the work has to be done physically and also mentally. So in physics, work has to be done with the force only. If some force has to be acting on some object, the work has to be done. How we know that the work has to be done in that object? It displaces. That means it covers some distances. If I'm giving some force to anything, like for example, I've given my force to a duster, it moves to some distance. That means the work has to be done over there. The force is acting on the object. That object moves from one place to the another place. That means it displaces from one position to the another position. Then the work has to be done over there. That is work. And for done this work, we need what? Energy. Energy is nothing but ability to do work. And how much work has to be done? That rate of work done is nothing but power. So these three things are related: work, energy and power, and that we are going to see in this lesson elaborately. First of all, we are going to see the topic work. So the work, let us consider a force F acting on a body which moves it by the displacement in some direction. In any direction it moves, right? So we are taken as some direction, that is dr. So that has to be shown in a figure 4.1 figure. So how this expression has to be done? That means we are giving some force to an object and it displaces and work has to be done. And that expression has to be given by capital W as denoted as work done by the force on a body is mathematically written as W is equal to F dot dr. So force with the direction, any direction, and that is given here. And the work done by the force depends on the force. The work done by the force is depend on the force, displacement and also the angle between them. So the work has to be work done by the force depends on the force, displacement, dr and also the angle between them. See this diagram, work done by a force. So a person is giving the force to an object and it moves. So see here, the movement has to be given here, that is dr is denoted as the direction, and then the F is nothing but force and the angle has to be made over here. So F cos theta. So here the product F dot dr is a scalar product or a dot product, and this is a scalar quantity. So work done is a scalar quantity. So you know what is the meaning of scalar quantity? It's have the magnitude but don't have the direction. What is it meaning? So it moves wherever the direction. It don't have the certain direction. So it does not have only one direction. It will have multiple directions. So that means no direction for the work done. It has a magnitude only. So you know what is an SI system unit of work done? That is a Newton meter. That is nothing but distance it covers and the force. So force unit is Newton and the displaces so meter. So Newton meter, and also the general is joule. So work done is always calculated by the unit of joule, and its dimensional formula is ml square t minus 2. So the work done is equal to F dr cos theta, which can be realized from the figure. So A dot B is nothing but AB cos theta, you know in the mathematics, where theta is nothing but the angle between the applied force and the displacement of the body. So the work done by the force depends on the force F and also the displacement dr and also the angle between them, that is the theta. And this is also clearly given in the next figure, that is 4.2, as an angle, how it makes an angle, that we will see. So see this diagram, F cos theta, W is equal to F cos theta dr, and here the dr is the direction and the displacement, and F is nothing but our force, and it makes an angle, and this is a F cos theta. So it have three cases, and we will discuss now. The work done is 0 in the following cases. When the force is 0, for example, if a body moving on a horizontal smooth frictionless surface will continue to do so as no force, that is not even friction is acting along the plane. This is an ideal situation. So if there is no the frictional force, then there will be zero force has to be acting. So in the first case, the work done, if force is 0, definitely the work done is also 0. That is the first case. In the first case, we discussed that as force is 0. So what that means, the work done is also 0. If there is no force, so the work done is also 0. And next case, the displacement is going to 0. For example, if you are giving the force to a wall, what happened? No change in the displacement. If you are giving your force to the wall, what happened? The wall is on the same place, so no displacement has to be there. So that means that is also 0. If displacement is 0, then the work done is also be 0. This is the second case. So in the third case, we will see this when the force and the displacement are perpendicular. That means theta is equal to 90 degree. When a body moves on a horizontal direction, the gravitational force does not work on the body since it acts at a right angles to the displacement. Likewise, in the circular motion, so in the centripetal force is there, but that centripetal force do not work on the object or moving on a circle, means it always be perpendicular to the displacement. So no force has to be acted over, so it takes the theta as a 90 degree. So in that case also the work done is 0. So now we are discussed as three cases. In the first case, the force is 0, and the second case, the displacement is 0, and in the third case, both will be perpendicular to the direction. So in perpendicular direction, the theta takes 90 degree value. So in that case also the work done has to be 0. See here, the diagrams has to be given. That means we are discussed as the three cases, no? So related to that, the diagrams has to be given. So first case, the F is 0. So for the second case, see the diagram of EA, and they are giving the force to the wall. So there is no displacement. So that is related to the second diagram. And for the third case, two diagrams has to be given. In the first one, it's perpendicular. See that the force is acting upward and the direction dr, and the gravitational force is downward, so that is the perpendicular. And see the last one, there also the centripetal force has to be, for the displacement it is perpendicular. So the forces are perpendicularly acting for the B and C, so it makes a 90 degree, so right angle. See here F and dr, and here also centripetal force on the displacement has to be right angle, so it makes a 90 degree. In that case also work done has to be 0. So related to this, one problem is given as an example of 4.1. A box is pulled with a force of 25 Newton to produce a displacement of 15 meter if the angle between the force and the displacement is 30 degree. Find the work done by the force. And see here, so angle is given, theta is given, and then dr is also given, and f is given. So everything has to be given, and we have to find out the solution. So see here the solution itself, we are given the force, that is the F is equal to force. So F is equal to what? F is equal to 25 Newton, and displacement dr is 15 meter, and then F and dr, theta makes as 30 degree. So the work done, W is equal to F dr cos theta, we already discussed. So in the place of all the F dr and cos theta, we are going to substitute the values. So F is nothing but 25, it's a straight substitution, and dr is 15, cos 30 degree is nothing but root 3 by 2. So we have substituted that value also, and for 25 into 15 we'll get some value and multiply, and then multiplied with the root 3 we'll get the answer as 324.7676 joule. So that is the work done has to be calculated for the example problem of 4.1. So next we are going to see the work done by a constant force. When a constant force F acts on a body, the small work has to be done, and that is taken as a dW by the force in producing a small displacement, that is taken as dr, and that is given in a relation, that is dW is equal to F cos theta dr. So the integral part, that is a small part we are taking, means we have to take an integration. So the total work done in producing the displacement from the initial position Ri to the final position of Rf. So the work done Rf is taken as a upper limit and Ri is taken as a lower limit, and then dW, and we are giving that W is equal to Ri to Rf F cos theta dr, and F cos theta is in no changing value, constant, so we are taken out and taking the integration for the dr only, and we know the upper limit and lower limit, that is Rf Ri. So the upper limit we are taking as these two, or F minus upper limit minus lower limit, and that is denoted here as a integration part. So the graphical representation of the work done by a constant force is shown here. So the area under the graph shows the work done by a constant force. So this has to be given in a graphical wise. So the graphical representation of this has to be given here. That is nothing but work done by a constant force is taken. Then the F cos theta is taken as a y-axis, and Ri Rf, that is the R has to be taken as a x-axis, and two limits has to be given over there, and that limit we are make as a constant force. So if we are draw the graph, means we are getting a constant force for the work done, and that is given here. So related with this, we'll see one problem, that is example problem number 4.2. An object of mass 2 kg falls from the height of 5 meter to the ground. What is the work done by the gravitational force on the object? So the neglect the air resistance, we are taking the acceleration due to gravity as 10 meter per second square. So the picture itself clear, that is one object is falls from height to the ground, and the total height is given, that is 5 meter, and dr is also given, and mass is given as 2 kg, and F is equal to mg, we know that, and the gravitational force is given. So what is the work done by the gravitational force on the object, and acceleration due to gravity is also given. We are going to solve this problem as. So solution, in this case the force acting on the object is downward. So we know that what is a downward force, that is gravitational force mg, and this is a constant force. So work done by the gravitational force, we know that total work done. So some part we are going to take as an integration. So Ri to Rf F dot dr, and we know that F cos theta and dr only changing. So we are taking the integration to that, from the lower limit as an Ri and upper limit as Rf, and that is equal to, and F is nothing but gravitational force here, and that is mg. So mg cos theta Rf minus Ri. So the object also moves downward, which is in the direction of the gravitation. So we are taking the force as mg, and the theta here, angle between them is nothing but 0 degrees. So what is cos 0? You know that how to calculate cos 90, cos 0 or cos 190. So always the cos 0 degree value is 1. And the displacement of Rf minus Ri, that is the total distance they are given as 5 meter. So all the values is given. So it's a straight substitution. W is equal to mg Rf minus Ri. M value is given as 2 kilogram, and 10 is nothing but gravitation due to gravity, that is 10 meter per second square, and Rf is minus Ri is nothing but 5. So total multiplication will get 100 joule. So the work done by the gravitational force on the object is positive. Next we are going to see the example problem number 4.3. An object of the mass m is equal to 1 kg sliding from the top to bottom in the frictionless inclined plane of the inclination angle is 30 degree, and then the length of the inclined plane is 10 meter as shown in the figure. So we have to calculate the work done by the gravitational force and normal force on the object. Assume that the acceleration due to gravity is equal to 10 meter per second square. So in this they are given the diagram clearly for the inclination angle and what is a normal force. N is a normal force and mg sin theta, that is the components results, and then mg cos theta is there, and then mg, that is the gravitational forces acting over here. Everything will be given clearly in the diagram. And we are going to calculate in the we are calculated in the previous chapter acceleration experienced by the object in the inclined plane is g sin theta. So according to the Newton's seconds law, the force acting on the mass along the inclined plane F is equal to mg sin theta. Note that this force is constant throughout the motion of the mass. So the work done by the parallel component of the gravitational force is mg sin theta. So here we are going to calculate the W, that is work done. Work done is equal to F dot dr, that is equal to F dr cos phi, because here theta is already taken, so we are taking that as cos phi, and where phi is the angle between the force, that is mg sin theta, and the direction of the motion is dr. In this case the force mg sin theta and the displacement is dr are in the same direction. So phi is equal to 0, that is cos phi is equal to 1. So W is equal to F dr, that is equal to mg sin theta to dr. Dr is nothing but the length of the inclined plane. So W is equal to 1 into 10 into sine of 30 degree into 10. So sine of 30 degree, and we are substituting the values of all these things and it becomes 50 joule. That is the answer for the example problem of 4.3.